we completed our panels, and then practically today will be is going to be should I say our when it comes to coding or writing codes. Today will be our last time, and then you we will be given our capstone project. So on our next meeting, what we will talk about will be how to actually use some AI tools to help you in your data analysis. So once you have data and maybe how you would like to use these AI tools, and then their purpose of usage is not for them to work for you blindly, but you yourself, when you how to use AI in data analysis together. And yes. All right. So maybe someone may say that if AI can do these things, then why bother to learn Python and all those stuff? So AI, when you use it, you will realize that they will tell you that it can make mistakes. Okay. So not that it makes mistakes though, but sometimes what it is doing based on the prompt that you give to it, it becomes hard for you to I mean, if you don't understand what it is doing and you can't read the code that it is implementing, it becomes hard. Yes. All right. So let's zoom in into what we have today. Okay. So in previous times, we've talked about Python data structures. So first data types and all the rest are data structures, which Python use in handling data. So once you have your data available in the right data structure, for instance, in Pandas, Python has a way of, performing some statistical analysis, such as hypothesis testing and then t-test, chi-square for categorical data, and also to find correlation between real data sets. Okay, so we initially learn how to upload a CSV file in Pandas. However, you can upload any file, including Excel files, or I haven't tried databases before, but I think it should be possible to query SQL files, which are databases in Pandas for analysis. All right, so before we start, the key thing or the major difference from packages that we've been using or the modules that we've been using is a SciPy. So the SciPy stands for Scientific Python, and in this case, from the Scientific Python, we want the start module. So the start module consists of a lot of functions, statistical functions that we want to use, because there is no need for us to write all these functions from scratch. However, it is better for us to use the packages that have been optimized to perform, that has been optimized for high performance. And then you can see that Seaborn 2 was not used in our previous studies. So Seaborn is an advanced form of Matplotlib, though that will not be covered in this course. But however, some of its implementation will be used to make some plots. However, the Seaborn package, most of the things that the Seaborn package can do, the Matplotlib can also do it likewise. So we specify the Matplotlib inline, and then we provide these parameters as default parameters for all our charts. So we run this first code to load our libraries. So once our libraries are being loaded, we begin to use them. So ideally in Python programming, we like to load all our libraries so that in the subsequent codes, we begin to use them. Now let's come here. So last week we learned how to import data. So we use the pd.read_csv. Okay, so this actually reads the data or the country Wise latest, which is a coronavirus data from my desktop directory. Okay. So once we do that, we can find the shape by using the df.shape. And then we can use the head to print the first 5. So this is actually our data which we are working on. And this data, as we can see over here, consists of 15 columns and 87 rows, which is the value, which is the information about the data given by the shape. So last time we also learned about an info, df.info, which also give us data about the information about our data set. All right. So we are not going to run it here. So, and even the describe give us the descriptive statistics for all the numeric or numerical columns. Once we have this data, it looks like as if it records the confirmed cases, death cases, recovered cases, active cases, and so on and so forth, based on country. In this country have been grouped under the WHO region, based on it, the continent it can be found. So Afghanistan is in Middle Eastern Mediterranean, and then Albania, Europe, and so on and so forth. So basically, it is the COVID records of each country, okay? And then the WHO assigns the continent where that country can be found. So that is how the data is. Based on this understanding, you can use it to perform some analysis. So descriptive statistics has to do with the mean, mode, and then median. So every statistics is built on your descriptive statistics, and so it's important for you to know them. So we can calculate for the mean, mode for each of the columns over here. How do we do that? So to calculate the mean, median, and then the mode for death per 100 cases, or the number of death per 100 cases, or that we need to say that we assign a variable called death rate to the column death df, which is the data frame, which we created here over here. Okay. All right. So the data frame or our data select the deaths per 100 cases column, and then on that particular column, we want to calculate for the mean, the median, and then the mode, and to each of them round it to 3 decimal places. When we do this, we are going to get the data, the mean, median, and the mode of that particular column. We can just change the column to something else, provided we want to find the mean, mode, and then median values of the number of deaths. So I think I can just clear this one. All right, so you see that the mean death rate is around 3,494. So that is, so most of the deaths cases are centered around this particular value. And then the median is 108 for that particular, and for the number of deaths. Okay. And then the mode rate is 0. So as in the highest, when you plot your graph, the mode is a number that occurs the most, right? And in this case, it is the 0. So the number of deaths, the number of countries with no death is higher as compared to the number of countries with death. All right, so in statistics, we have something that we call dispersion. When you talk of dispersion, we are talking about how our data is being dispersed. And so we have the variance, the standard deviation, the range, and then the interquartile range. The variance talks about how the data points of our data vary from one another. So for instance, when I say df.head and I print first of that, when I choose the deaths column, or maybe the confirmed, or any of the numerical columns, if I want to find the variance, the question is, how is this data point under the depth column different from this? Okay, data vary from each other. That gives you the variance of a data set. And the standard deviation also gives you, or tells you, how your data is being how far is your data point from your mean. Okay, so once you have your mean value, how is the data spread around the mean? So once you have that, then the range has to do with the distance between the highest value and then the minimum value that gives you the range of that. So in this case, if you are able to, let me just use the let's say okay, I think the code is here, so why should I write it? So we can get the maximum value, okay, by just writing. Let me just write the code. I just want to use a different variable. So let's say df, and then I say confirmed cases. Okay, I can say dot mask. Okay, that's going to give me the maximum value. Okay, and then the main will give me the minimum value. So I can say df. Let me say confirm cases, and then I'll say dot main. So what I'm actually doing over here is that I'm subtracting the maximum value of this particular column from the minimum value. And so once you perform that subtraction, that will give you the range of your data. So this tells you how, it also tells you the dispersion of your data. Okay, so if the range is wide, you know that the column that column you're working with contains high values. However, if it is okay, I think this love is one. So you see that. Okay. So you will see that the minimum value is 10 under the confirmed cases, and then the maximum value is around 4 million. So you see that the range of the data is so wide. Okay, this also gives you an idea of how dispersed your data is. Okay, so we can also move on to the variance, and then the variance to check for the variance, you just use the var method on your column. So you know, record that the data rate is assigned to the depth. Okay, sorry, depth rate. So it's assigned to the depth column as we defined over here. So the depth rate, so we want the variance of the depth rate rounded to 3 decimal places, and then also the standard deviation. And then the quartile, interquartile equals to depth rate dot quantile. So 0.5, depth rate quantile 0.575. So this quantile method actually retains the quartile range that you want. So this 0.25 is the first quartile range, and then the 0.75 is the third quartile range. So the difference between the third and then the first will give you the interquartile range. Which one or the other also tells you about how dispersed your data is. All right, so we have the variance to be around, this value, and then the standard deviation, so how distance the data points are from your mean. Okay, all right. So it's calculated and then it gives you that plus or minus value. And then you have the range, okay, which is the difference between the highest and then the lowest value. Then you also have the interquartile range, which tells you about, it groups your data into percentage, as in the percentile, 25th percentile, and then the 75th percentile. And then it retrieves for you the interquartile range. All right, so we also have the skewness and kurtosis, which has to do with the distribution of data. So data distribution, how distributed data is crucial in statistical analysis, such as the t-test and then the ANOVA, because if most of these statistical tools assume that your data is statistically your data is normally distributed. Okay, so let's see something over here. So we want to calculate the skewness and then the kurtosis of the confirmed case column. All right, so the raw code is just this one. So we are just rounding. So we just have to select the column. After selecting the column, we say dot skew. So this calculates for the skewness of that column, okay? And then the kurt calculates for it also calculates for how the distribution, okay? But it actually implements the kurtosis method or approach. So we round it to 2 decimal places. And then we just make a plot that is a histogram, because initially I told you that the histogram helps us to know the distribution of the data, and it tells us whether it is normally distributed or it is not. So when we run this code, we can see that the skewness of confirmed cases is 8.73, and the kurtosis is actually 8.61. And then we plot the values in the confirmed cases. So we can see that we have some independent values here. However, the place where the value is centered is around 0 to, let's say, 0.5. Okay, and then from here we use the axv line to also indicate the mean and then the median, where we color the median red and then the mean we color it green. So maybe I think yellow will do, since it will make this one more not as I thought, but at least it's okay. So we have the mean over here and then the median. So based on this, you can say that the data is not normally distributed, so it is skewed. Okay, yeah. And then that skewness is 8.73. Okay. All right, so we are going to talk about normal distribution and z-scores. So before we can perform some analysis, we have to figure out about the distribution of the data. One way that we did that was to use the skewness and then the kurtosis, and as well as the histogram. So in this case, we are going to just calculate the z-score, okay? And then in this case, we are going to use the stats that we imported from the stats model at the beginning of the code. So we say that df confirm z-score equals to start z-score. So we are calling for this z-score function from the start module. Okay, so and then we want to calculate the z-score for the confirmed cases. And then after we do that, we now filter it. What's the criteria for the filtering? We want countries more that have so countries that have more than 2 standard deviations above the mean confirmed case count. So we are just filtering out all countries that have more than 2 standard deviation. And so we provide it here. Okay, and how do we do that? So we know that the DF confirmed z-score calculates the z-score for the confirmed cases. And so once that the z-score is being calculated, now what we can do is to filter it using the data frame. So when we filter it using the data frame, we want to filter out the countries that have more than 2 standard deviations above the mean confirmed case count. Okay. And then once we do that, we select the countries that we would like to include. So if you recall, this actually creates a new column, which is being added to our original column. And then this column will have the z-score calculated for each of the countries. Okay. And the z-score answers how many standard deviations away from the mean is this value. Okay, so it picks each value and it calculates for the standard deviations, the number of standard deviations away from the mean value. So that is what the z-score is doing. And then afterwards, then we are filtering all countries that have more than 2 standard deviations above the confirmed cases. So it means that we have to use the z-score, which calculates the number of standard deviations away from the mean. So once we do that, we select the countries that we would like to include in our data or data frame, and then we sort it using we sort it in descending order by choosing the ascending equals to false. So when we do this, this is what we have. So these countries are called outlier countries, okay, because they have more than 2 standard deviations above the mean. So that is a criteria that we have given to it. So all outlier countries are countries that have more than 2 standard deviations above the mean confirmed case count. Okay. And then so we have these countries as outliers. So we have the United States and then Brazil and then India. So all that we are trying to say is that their numbers are extremely high. Why? Because when we calculate the standard deviation for the confirmed case column, like the number of times that standard deviation is away from the mean, these values are more than twice of the standard deviation. To confirm this particular code, let's try to see whether we can get the standard deviation of the confirmed column. Okay, .std. Okay, so actually this becomes the standard deviation, but the z-score also applies some statistical manipulations, which scales this one down. And so apparently by scaling it down, these are the values that have standard deviations, that is more than twice, okay? So that is, like it has, the standard deviation, like they are more than 2, okay? So as to when you compare this, the z-scores of each of the countries, because the z-score applies some scaling to the data or to your values. That's why they are small compared to the standard deviation, which does not involve any scaling. However, when you use the z-score in the scaling, as it scales down your value, you realize that these values are these countries have two more than two standard deviations above the mean. Okay, all right. Likewise, when you calculate value, you realize that it's also a higher value. So how is the z-score smaller values? So that's what I mean by the scaling. Okay, so basically, that is that up to this stage. So please, can you, if you have any question, you can ask up to this stage. And please, any questions so far? If you have a question, you can ask. If not, so we will make progress. Please, can I get a feedback from you?
Please, I have no question.
Okay. All right, so that is that. So the z-score tells you how many standard deviations a specific data point is away from the average. So, like, um, I mean, once you have your data, as we saw from here, so it picks just this data, and it calculates how many times, how many standard deviations this particular data is from the mean, and it calculates the standard deviation. And we realize that for US, Brazil, and India, they have standard deviations more than two away from the mean. Okay, so that gives them, that makes them an outlier based on the criteria that we set. Maybe based on what we need for our data, we can set it to one, but in this case, two, just for learning sake, because it will vary based on the kind of analysis you are doing. Okay, so we also have this normality. Okay, so we would like to also check for the normality of our data. Okay. And I hope we all know what normality means. So normality tells us whether our data um, is normally distributed. Okay. Let's run this code so that I use it for the explanation. Why is this not taking so long? Okay. All right. So we are checking for whether our data is normally distributed. In this case, we are using, okay. So in this case, we are using the death rate, so the number of death per 100 cases, which gives us the death rates from our COVID data. So we want to see whether the death rate across the countries or across the continents is normally distributed. The data is normally distributed. So how do we go about it? So we try to make a plot and then using that plot to check for the normality. So you see that for normality, ideally it's supposed to have a bell shape, okay? So once you plot this,
Daniel. Daniel.
Yes,
Mm,
please. Yeah, Grace, come again. Hello, Grace. I think maybe your network, so you can type it in the chat and then I'll respond. All right, so we just create a variable. It is just like creating these variables individually, but you can just put it together and separate
mhm.
them by column, comma.
Daniel, please, can you
What
hear
will
me?
happen is that,
Mm,
yes, I can hear you now. So Grace, if your network is not helping, you can put it in the chat and I will do all to take a look at. Okay, so you just assign the variable. So we are just, this particular code is like saying that mu equals to data, which is the def per 100 cases or the def rate column, data mean, and then going to the next line and creating sigma equals to data dot std. That's that. So this implementation is the same as this. Okay. Just that this one gives you one line and then it makes your code more compact. So we assign this value this to that. So it's mu will be the mean of the def column and then the sigma will be the standard deviation of the def column. We create our figure and then the axis uses the subplot. So we did not specify any fixed size over here because if you recall from the beginning of the code, we specify the all those parameters using the RC params of the matplotlib package or module. So we are going to plot a histogram. So if you joined last week, you realize that a new implementation of matplotlib is not using the axis. However, we can plot using the data. So using the columns. So we are saying that this data dot plot. So on the def case, def per 100 cases data plot, make a plot. And what type of plot? The kind of plot is a histogram. And then the number of bins, okay, which is the interval, should be 25. And then we assign density to be true. And then color, and then we provide all these parameters. And then we set the axis to this axis that we've created using the subplot. And then here to draw the line, what we do is that we use the np.linspace. So the linspace creates values that are equally spaced between the minimum and then the maximum value. And in this case, we need 200 values. Okay. All right. So the next one is the act and the plot. So if we are if we have created this x value, okay, which gives you values between the highest value in the number of def per 100 cases column. So the minimum and then the maximum, and then it generates 200 values that are equally spaced between these two values. And then we are saying the ax.plot. In this case, we are plotting these values that are equally spaced between the minimum and then the maximum value. And then then we call the start function. So we say that start.normalize. So if you recall, when we were doing pandas, we were doing something like normalize. And I told you that once you have the normalize, you use your standard deviation and then you use your mean and also the data that you are using. And you are going to, we want to normalize your data across. So in this case, we are normalizing across this particular data using the mean of the data and then the standard deviation. Okay, so it's going to provide values based on this particular data that we have here, which has been generated from the column. Okay, using our standard deviation and then our standard deviation and then our mean. We provide these color parameters and then a label to it. Once we done, then we plot it. So this is what gives. So this line over here, drawn over here, was implemented using this code. And then the first one helped us to get that smooth line, okay? Because The reason why it is smooth line is because the values are consistent and equally spaced. So it enables us to draw this particular smooth line. When you look at this line, you can see that the data is not normally distributed. It looks like it has skewed to the right-hand side, okay, when you are facing away from the screen. So it's not normally distributed. So you can see that the depth redistribution is not normally distributed because the normal curve is supposed to be a bell shape, which is not seen in this particular data. Okay, so we also have another one that you can do, which is the QQ plot. Okay, so the QQ plot also helps us to
Daniel,
yes,
please can you go over the one before?
this one.
Yeah.
Okay, so please, which part?
Or from the visual, like from the beginning. I wasn't here because of the network.
So I was saying that first, we want to check for the normality of the depth per 100 cases. So that is a column of the data. You want to check whether that data is normally distributed. And so if you want to do that, instead of calling this one each and every time in our code, we actually don't want to do that. So we assign a variable called data to represent the column. And then we use the mu and then the sigma 2 as variables for the mean of the column and then the standard deviation of the column. Please, you get it up to this stage.
Yes, please, I do.
So once we are done, then we specify the figure and then the answers. And then how do we do that? So we know this one for matplotlib. And I said that you're not going to provide that fixed size that we used to do because we've done it already at the beginning of the code, of our notebook. So we move straight ahead to the plot that we want to make. In this case, for us to check for the distribution of the data, whether it's normally distributed or not, we need a histogram. So we say that on this column, which is the data assigned to the column, so you say that this column, we want a plot on this column. And the kind of plot should be histogram. It should have 25 bins, as in 25 intervals. Then we set the density to be true. And then we set all these parameters, color, and then alpha as in opacity. And then ideally in matplotlib, we are going to say that ax.plot. Then we provide this, and then we will use this data as an argument. However, we are inverting things, or we are implementing the matplotlib in a different way. And I think this is optimized when it comes to data frames compared to like the list that we were working with previously. So in this case, what you do is that you assign the ax to this ax to tell him that we are using the axis created by the PLT, the subplot. So once you are done, that will give you this blue thing over here, which is your histogram. All right, so when we are done, we need to check for the normality. So if we get a curve that tells us whether it is normally distributed or not, that will be better. Because the curve, looking at the curve alone, can even give you a visual representation other than just reading or maybe using intuition or discretion to say that this data is normally distributed. So in order to make this particular curve, we generate 200 values between the maximum and then the minimum value of the data point in the depth per 100 cases. And when we use the length space, it creates these 200 values and in such a way that the values are equally spaced. So one value is different, is equal to, the difference between, okay, let me just make an example over here. So when you pick these values, you realize that the difference between 2 and 1 is the same as 3 and 2. Is the same as, so those are the values that it creates between the minimum and the maximum. And then we need 200 values. So you will realize that this will cover all data across your data frame because we are taking the minimum and then the maximum. So it will actually capture every particular data point. And then once we are done, we make a line plot, okay? The line plot. So the line plot, we have our y-axis and we have our x-axis already stated. So what do? We provide this one as the x-axis, which are the data points over here. And then we normalize our data, the data over here, using our mean and then the standard deviation. Okay, so by normalizing it, it means that we are going to plot the distribution of this particular values. Okay, so once we do that, it's going to give us this particular line, straight line, smooth line. Okay, so once we have that smooth line, then it will give us a fair knowledge of whether our data is normally distributed or not. And normally distributed data should have that kind of a bell shape. So in this case, you see that there's where line goes and comes here. But like the data point is centered at some, like the left side of the curve. However, it should be in between. And so these tall bars, or these tall values, these tall bars of the histogram should be in the middle, and then there should be data on its left-hand side and the right-hand side, which makes it normally distributed. But however, we don't see that in this case. So it means that that particular column, which is the depth per 100 cases column, is the distribution of the data is not normal, as in it is skewed. Okay, in this case, to the right, when you look away from your screen. I mean, like when you look away from your screen, it is on your right, so the data is skewed to the right. Please, you get it?
Yes.
Okay. And then I was talking about the QQ plot, which is also help us to test for the normality. Okay. All right. So that one, it just uses some line, then also a curve, but it's not as cumbersome as this. Let me just run it so that we see how it also behaves. So this is how the QQ plot is. And this blue thing that we are seeing over here are the data point, and this is the line. So if the data is normally distributed, all the data points will be on the line. Let's see that. So this is how we implement it. We say that we create a figure, and then this one, we want to control it. We want to override the default fixed size that we've set already. So we provided this. And then we say that start.prob plot, okay, which is the QQ plot. And then we are using the data, which is the column, the depth rate column. And then the distribution, we want a normal distribution, okay? And the plot equals to the axis, which is this, okay? So once we specify that, we just set the title, and then we say plot.show. So once we say plot.show, it's going to give us this graph, okay? All right, so if the data point sits on the red horizontal line, we can say that the data is, or that particular column is normally distributed. But you can see that this one, it doesn't sit even from the beginning. It has deviated from the red line, and then it just crosses it and deviates, and so on and so forth. There is a bigger outlier over here. So this also helps you to confirm if this one is difficult for you to read, or to tell that your data is normally distributed. The QQ plot makes it simpler, because this one, you are just considering the data, you are matching the data points, which are the blue point, against the red line. And the QQ plot, the stats.prop plot handles everything for you without you having to create your own line, as we did for this one. However, this implementation is super simple, and it can be used on any data set. All right, though we don't have enough time, but I'll try to use a different column. So in a different column, the same data, but we are just changing the column to let's say we want to find a distribution of the confirmed cases. Okay, so once we do that, the confirmed cases is going to be, we are going to have the distribution. Now look at the distribution of the confirmed cases. It's not normally distributed, okay, because we only have a very one tall bar and the rest of the data is just right to it. So the data is not normally distributed. It is skewed to the right. So we can check for multiple. So to check for multiple, we just need to pass this as a list, and then that is going to work for us. So for the sake of learning, let us stick to our def 100 cases. Okay, because this one gives us, a better view of the distribution. Okay, so that is how you check for normality visually. Please, any question up to this stage? Okay, so if there is no question, we will make progress. So we have what we call the Shapiro work test or Shapiro work test. All right, so we've used the histogram to test for the normality of our data. But the Shapiro work test also checks the null hypothesis that a sample was drawn from a normal distribution. So what it tries to check is if a data sample comes from a population, like does a data sample, so let's take one column. So when you pick that particular column, let's say our def per 100 cases, it tries to check, this particular test tries to check if a sample or a data sample that comes from this particular column has a normal distribution. Okay. All right. So let's try to run it and then we will have a view of it. So if we want to implement it, we just use the start and then p-value. The reason why we are using the start and p-value is because this start dot Shapiro, when we apply it to our column, okay, what happens is that it retrieves a tuple which are a tuple of two values, okay, and we are assigning the first value to the start, which is actually the statistic value, and then the p-value of that particular column. All right, so what is the condition? These are just formatting. So let's come to the condition. So our alpha is actually 0.05. So the alpha also represents the p-value, okay. All right, so the set or the standard p-value. So if our, the statistical significance value, okay. So if our, in this case, if our p-value, which we will get from the Shapiro test, is less than the alpha, okay, then we can say that we will reject the hypothesis. The data is not normally distributed. However, if the p-value is actually greater than the alpha, which is this, then we are going to fail to reject because there is no evidence against normality. That is, the data is normally distributed, or it assumes a normal distribution. So in this case, let's come back to what we did over here. So we realize that when we run the start.Shapiro on our def column, def per 100 cases column, we get the statistic value and then the p-value. However, the goal over here, what matters to us is the p-value. So here, the calculated p-value that this one does for us automatically is 0.000. However, when you look at this 0.000, you see that it is less than our alpha, which is the statistically significant value. So once we do that, once it is less than the 0.05, then it means that the sample that was taken from this particular data does not assume a normal distribution. And so we will reject the hypothesis that the data is normally distributed. So it's like before you run the Shapiro, it's like you have a hypothesis, okay? So the hypothesis will be that the data is normally distributed, okay? So if that is my hypothesis, I have to justify it or reject it. And it has to meet a particular condition. And this is basically the condition. So you realize that we are talking about a lot of statistics. But however, the code implementation is as simple as what we've learned already. Okay. The only thing, there's nothing that is so new. The only thing that is new is just the start.Shapiro, which we know that it is a function. The Shapiro is a function imported from the start model that we imported. Just as you will say that df dot maybe group by, okay, please you get it? So maybe something like this. So it's something that we know. So actually the most important thing is to like understand what the test actually do. So in this case, we'll reject the hypothesis that the data is normally distributed because the data is not normally distributed. So the relevance of these things we will get to know. Okay. All right. So I mean, I hope it is all these ones are.
Hello. Hello, Dan.
Yes, hello.
Can you hear me?
Yes, I can hear you, Gloria.
So is the same as Minitab?
No, it's not the same as Minitab. So
It's different from Minitab.
yes, please.
Hello, please come again.
So it's different from Minitab.
Oh, okay. Okay. Thank you very much.
You're welcome.
Okay.
So basically, it is the same Python that we are doing. So Minitab is, I think it's a software in its own, and those are SPSS. And even R is it's a programming language on its own. So this is Python. And so Python has all these functionalities to perform all these things with this just simple line of code. Okay. So these ones have been created by some people. So, I mean, they all do that to help us so that you don't implement every code yourself from scratch. Okay. So all that you need to do is to know what you want. So as I've been saying earlier, there is no need to memorize all these things, okay? Yes, so your mind can do something better. So all that you need to do is to have an idea. And because you have been exposed to this, you know that this thing can be used to this, or there is this functionality in this. So how can I get it? So it helps you to know, okay, so you know that, oh, there is Shapiro. So maybe you want to test, because the normality is essential for some statistical analysis, which you will get to know. So these ones are just readable, so I'm not going to go through the ones that pertains more to what we have to. I'll just highlight it. But once you have the notebook, you can just go through it for your own understanding. So we go to the confidence interval. So a confidence interval gives a plausible range for the true population mean built from your sample. A 95% confidence interval means if you repeat this sampling process many times, 95% of the intervals you build this way would contain the true population. So it has to do with sampling, okay? So and we have types of statistical sampling, okay? Way that we sample data from a population. And then we are saying that if there is a 95% confidence interval, what it implies to the sampling that you've done is that 95% of the intervals, I mean, the intervals that you would that you like, I mean, in terms of the sampling of the data, as you are sampling the data. So when you employ that particular sampling process, which has that 95%, that 95% confidence interval, then we are saying that once you do that, then that particular sampled data will contain the true population mean. And that is the goal of sampling. When you sample a data from a population, the goal is that the sampled data will be at least, if not exact, will be close to or will represent maximally the population. Because if the sample data deviates far away from the population, and how can you say that based on the experiments or the data that I have, this how can you say that the outcome that you've had refers to the population? So always a sample should project the population. It should reflect it. And then if you have if you perform a sampling and you have a confidence interval of 95, then it tells you that that sampling method is actually good because it helps you, like, I mean, it contains the true population mean, if not close to the true population mean.
Daniel.
Yes.
Daniel.
Yes, Grace.
Daniel.
Grace, I can hear you. I hope you can also hear me.
Daniel.
Okay. I guess maybe.
Oh no.
Yes. Grace, I can hear you. Please.
Please, I'm joining from another device. Can you bring me into the call? I want to leave this meeting and join from another device. So please bring me into the call.
Yes, please. So you can do that. James will join you. Will add you. Or how can I say join? By the way. So yeah. So that is what the confidence interval says. I mean, what it tells us. Okay. All right. So when we have a single confidence interval, we are saying that we will not know, I mean, if we resample, I mean, so when we perform resampling, so maybe we go back to, maybe it can be an experiment. Okay, let me just use an experiment. You are sampling from maybe some microorganisms or maybe something. Okay, maybe people provide us a clinical trial and you are resampling and you have a single confidence interval. When there is a change, you will not actually, I mean, when you have a single confidence value, okay, it will not be able to handle that variation properly. So that's the reason why we need a confidence interval. So it expresses that change, okay, that variation, because when you resample, definitely there is going to be variation in your data. Okay, so the confidence interval is able to express that using the standard error of the mean. Okay, I mean, these are some statistical terms, so maybe you might not understand now, but once you have the notebook and you're going through, you can give your time some space to understand it thoroughly. So let's implement that and then let's see. So we assign the data to def cases. All this one we know n equals to len of data. And we know that this one will return the number of data points in this particular column. We calculate the mean, we calculate the standard error of the mean, okay, which is the standard deviation per the square root. Then we are calculating the confidence interval. So confidence interval low, confidence interval high equals to, we are using the same start package. So start.t.interval. Okay, so start.t.interval. Then we provide a confidence level 0.95. Then the degree of freedom is n minus 1. That's how the degree of freedom is calculated. Then we say that the mean is mean, and then the scale is the standard error of the mean. So once we are done, then we print our mean and then our low and high confidence interval values. Cases, the spelling. Okay, so we are done. So the interpretation of this particular code is that we are 95% confident the true average or the true mean death rate across all the countries lies between these two numbers. So the confidence interval is telling us that. So we know that's the projection to the population, okay? And then we are saying that based on our calculation, which was handled by the start.t interval, providing all these parameters, we are saying that we are 90%, 95% confident, okay, by providing the confidence interval ourselves. So we are, that is the 95%. We are 95% confident, okay, that the true mean of the death rate across all the countries lies between 2.521 and then 3.318. Likewise, when we change it to, let's say, 50% confidence interval, 50 will be 0.5. You see that now the values changes. So it means that the true mean of the population will be between these two values. Okay. All right. So that is that for confidence interval also. So it helps us to infer to our population because, and it has to do with your sampling. Okay, so once you sample and then your confidence interval is very low, then it means that if the confidence interval is low, then it means that the range in which your true mean will fall is going to be also wide. Okay, and then that can influence the outcome of your experiment with respect to the population. Okay, so let me set it back to the 25 and then 95 and then let's move on. So we have the one sample t-test. So the one sample t-test compares the mean of your so it tries to ask the question, does the mean of your sample differ from a specific known mean or hypothesized value? So there are times that there will be values that have been hypothesized, or there is a mean, a particular threshold, or a benchmark that is known. So you would like to perform a one sample t-test to figure out whether your mean, the mean of that particular sample, differs from the threshold. So in this case, we have a question that is the average death rate across countries significantly different from a widely cited early pandemic benchmark of 3 deaths per 100 cases. So the rationale here is like, okay, so there have been some pandemics in previous years. Our question is, does the average death rate that we have across the countries, okay, for COVID-19 pandemic significantly different from the the wide accepted, or maybe the threshold that we were able to come about or hypothesize for previous pandemics, and which has a value of 3.0. So we want to check whether the deaths over here, the average as in the mean, is different from this. So what we do is we use the start.t-test underscore one sample, which reflect the name. So it returns a tuple of your start and your p-value. We provide the data, which is this one, as an argument. And then you say that the pop mean equals to benchmark. So the benchmark, the pop mean actually is the threshold, okay, or the benchmark that you are comparing the mean of your sample with. So we say that sample mean death rate equals to death rate dot mean, and then benchmark equals benchmark. So we are just assigning variables to all these things over here. All right, so let's see how it works. We have our significance value of 0.05. Now we have a conclusion over here. We are saying that reject the hypothesis. Okay, so then in this case, the hypothesis will be that the average death rate across countries of this particular pandemic is different from that of early pandemic, which has a benchmark of 3.0. So that becomes our hypothesis. All right, so how do we reject and also fail to reject? So in this case, if our p-value calculated from here is less than our alpha, which is the significance value, then we are going to reject it. However, if the p-value is greater than the 0.05, we will fail to reject the hypothesis. So let's see. So in this case, we will fail to reject the hypothesis. Why? Because our p-value over here is far greater than 0.05. So by this, you can say that, so since we fail to reject them, we can say that the average death rate across the countries for COVID-19 is different from the widely cited early pandemic benchmark of 3.0 death per 100 cases. So it is also an insight that, or a conclusion that you can come up with using the one-sample t-test. The independent two-sample t-test. So that this is the test. So let me just skip that part. So comparing the means of two separate unrelated groups. So let me just try to call our data frame so that we get to know. So df.head. Let me just print the first two. All right. So when we see our data like this, okay, there are some columns that are unrelated. Okay, so we can try to figure out the relationship, like deaths and then the recorded cases. These are unrelated. They are not related by any means. Okay. All right. So there could be group or control or anything. Okay. So let's see how we can implement that also. So to test the means of two independent or two separate and unrelated groups, what we can do is by first selecting those groups and then second comparing them. So in this case, we will realize that these countries have been categorized based on the WHO region. So it has been categorized into regions. Previously, we were able to categorize them by tagging them, whether their values are low or not. However, in this case, that's not what we are doing. We are not creating any new columns, but we are using the WHO region. Let's see the code implementation. we want to find the correlation, or sorry, we want to test, we want to compare the means of the deaths in Europe and then the deaths in Africa and America. How do we do that? So we see that, so we have the DF over here, and then we are subsetting. Okay, so we are saying that DF WHO region. So for the WHO region, as in the column, select that column and select all columns, so in the WHO region column, select all data points or all strings that are equal to Europe. So it will look up from this particular region. Let me make it the first thing so that we can appreciate what I'm saying. So the first thing is that we have different continents over here. So Europe. So when this code actually is saying that, what this one is doing, this one, DF WHO equals Europe, say that for this column, select all the data points or all the rows that are equal to Europe, that are equal to Europe. And for that, select the def cases. Okay, so the DF of this, select the def cases. So here in this case, it's going to select all the def cases for all rows that have Europe. So all rows that have Europe, their def cases will be selected. And then the same thing is done for the America. So once we are done, we have two separate and then unrelated groups, because America and then what's the name? Europe are not the same. They are separate. Okay, so we are going to use the 11 test to check whether they have equal variance. Okay, and this is how we implement it. So we say that 11 start, 11p, which gives you the 11p value. And then we see that start.11. So we provide the sample 1, which is this one, and then the sample 2, which is this one. Okay. Now, what is the criteria for we to say that they have equal variance or not? So we say that equal variance equals to 11p greater than our significance value. So instead of creating an alpha, we are just assigning it directly. So if it is greater than or equal to 0.05, that is when they have equal variance, and then vice versa if they don't have equal variance. So let's run this one and see. Okay, so when we say equal, when we check for whether they have equal variance, the answer is true. Okay, so this is a condition. So if the 11p is greater than or equal to the 0.05, it's going to give you, is greater than or equal to 0.05. It's going to give you a Boolean value, either true or false. Okay, so if it is true, then it means that they have equal variance. If it is false, that is if it is less than or equal to, or if it is less than, so it cannot be equal to, if it is less than the 0.05, then they do not have equal variance. Why is this particular testing appropriate? This is appropriate because ANOVA and then t-test require that groups have equal variance. So if you want to do independent t-test, the two groups should have equal variance. Okay, so if the two groups should have equal variance, there should be a criteria to check for that. How do we do that? We use the 11 test to check whether the two groups have equal variance. Please, I hope we are following. Okay, so once we check and then they have equal variance, then we can run our independent t-test. How do we go about it? So it's the t start p value equals to start dot t test underscore independence. So we okay, so once we we are able to figure out whether they have equal variance, then we can move on to the independent t-test. However, there is something over here. So if they don't have equal variance, and we want to still perform independent independent two sample t-test, then we have to use the Walsh test. Okay, that is only if and only if the two samples or the two groups do not have equal variance. Okay, because once they do not have equal variance and you use the independent t-test, your values will not be accurate. So that is not what it's meant for. So we use the Walsh test. Okay, all right. So that is when provided it does not have equal variance. Okay, so we run the t-test and then that is that. So we provide this and that, and then we say equal variance equals to equal variance. And then that is true, okay? It's true over here. So you say that equal variance equals to true. So once equal variance equals to true, then what do? We are just going to print the mean and then the length and then all this stuff. Then, I mean, these are just some formatting. So let's consider the condition. Our alpha value, significance value is 0.05. So if p is less than alpha, with this p value that will be obtained from this expression is less than alpha, then we are saying that reject our hypothesis. Europe and the Americans have significantly different mean death rate. Else, you fail to reject the hypothesis. So you see that these tests are used to test for hypothesis. You should always have a hypothesis. All right, so let's try to visualize a comparison. Okay, so we are just using a box plot. Something simple over here. A box plot to, check our hypothesis or visualize our conclusion. That is, they have significantly different mean rate. So when you take the box plot, please, I hope you guys know how to interpret a box plot. Okay, so this part of the box plot is the 20%. Yeah. Yes, James. Oh, okay. So this one is the 20. What's the name? All right. So sorry. So when you take this particular box plot, for instance, this gives you the minimum, and actually the top gives you the maximum, and then we have the whiskers over here, and then you have your lower quartile range, which is the Q1, which is the 0.25 or the 25th percentile, and then you have your median value, okay, and then you also have your upper quartile or the 75th percentile, and then you have the maximum. So these ones above the maximum are called the outliers. So for Europe, we have a lot of outliers compared to the Americas. Okay, but however, when you look at this particular data, you realize that the median of the value in the Euro box plot is different from that of the Americas, right? Because when you look at the interquartile range, which is from here to there, that is from the lower quartile and then the upper quartile. That gives you the interquartile range. So when you look at it, you see that the mean of the Europe is somewhere around the middle, but you see that for the Americans, the mean is somewhere around the top. So this gives you like, this confirms the independent t-test that telling you that the two groups, which is the death rate in America and then the death rate in Europe, their mean values very different. Okay. All right. So per t-test, I want to finish, but it looks like I can't finish. So we need to end here and then we will continue on Sunday. But I would like to show you the assignment, though I will post it on the class page for you too. I mean, as an assignment, our capstone project. So let me just open it and share with you shortly so that you can start prepping for that. So we will pause at this place. We will continue the paired t-test on our next meeting.